Well, good morning. We'll be getting started in just a couple of minutes. I want to make sure that you can hear me. So if you can hear me, please click on the raise hand sign on your control panel. Okay, good. It looks like you can hear me. So it's 10 o'clock, so let's start the webinar. My name is Pat Whitcomb. By training, I'm a chemical engineer, although for the last 40 plus years, I've been working primarily in the area of statistics and design of experiments. And I'm the founder of StatEase Incorporated. Although I'm mostly retired at this point, I do still do a few things for them, and I'll be presenting this webinar on robust design, propagation error, and tolerance analysis. To prevent disruptions, all the attendees will be muted. If you have questions, you can post them in the question area, and we're lucky in that we'll have our workshop manager, Sherry Kraber, monitoring and answering the questions during the webinar. If you have questions that occur to you after the webinar, you can send those to stathelp@statease.com. When you send an email there, please provide your company name and information about whether you're using Design Expert. And if you are using Design Expert, please include the serial number, which can be found under the Help About. The slides and the recording of this webinar will be posted on the webinars page on the StatEase website in a few days. So let's get started with the webinar. I'm going to be talking first about general concepts associated with robust design. Then I'll get into the main tool that we use at StatEase and is programmed into Design Expert, and that's the propagation of error. Then I'll go through an example using propagation of error and use that example to illustrate tolerance analysis. An example we're going to look at are machine parts, and that should show how the tools can be put to use. So what are the robust design concepts? Well, when I learned DOE, and I think when most people first learn DOE, they really learn it to do functional design. Functional design is when you use designed experiments to determine a mathematical relationship between the inputs that you're controlling and the outputs, the responses, and develop a mathematical model. Then you can use that mathematical model to change the levels of the inputs to achieve the targeted values you want on the responses, the outputs. Robust design goes a step beyond functional design in that we also consider as a response the variability. And the variability of the output can be considered as a function of both the controlled factors, the factors you're controlling in your experiment, and uncontrolled factors. Those might be environmental factors or other things you can't control that contribute to the variability in the input. And the idea behind robust design is we want to choose the level of these control factors, not only to achieve our target as we did in functional design, we still want to do the functional design, but we also want to choose levels of the control factors that reduce variation in the output. And that variation in the output can come from several sources. We're going to consider two. One is the lack of control of the control factors. So when we're running experiments, we can control the inputs to those experiments usually quite well. But after the experiments, when the process is moved into production or into general use, there can be some variation of the factors. So when we talk about controlling factors, what we're really doing is controlling their set point. And there's variation that occurs around those set points. There's also variation that can occur from uncontrolled factors. So those are things that aren't part of our experiment and either are beyond our control or we choose not to control, and their variation can also affect the output and cause variation there. So what we want to do when we do robust design is we want to choose levels of the control factors. So definition of the control factors are the parameters whose nominal values, or I could say whose set points can be cost effectively adjusted by the engineer. So an example of that might be we're running an oven, we can change the setting for the oven temperature. Okay, so we want to choose levels of the control factors in a way that reduces the output variation. In other words, make the product, the process, or the system robust to variation in the inputs. And we also want to do the same thing for uncontrolled factors. So uncontrolled factors are parameters that are difficult, expensive, or in some cases impossible to control. So an example of an uncontrolled factor might be the ambient temperature. Okay. So controlled versus uncontrolled factors. Determining a factor is uncontrolled or a controlled one depends on the team's objective and the scope of the project. So a factor could be considered controlled in some cases, and that same factor might be considered uncontrolled in other cases. So for example, the hardness of a material measured by the durometer, for a design engineer who's choosing the material, that durometer becomes a control factor. I get to pick the stiffness or the hardness of the material. But once that material's set and it's put into production, the variation in durometer around that specified value is uncontrolled to the process engineer, who only sees the variation within that chosen material. Okay, so there's some variation around that set point. So how does propagation of error fit in, or what is propagation of error? So when we talk about propagation of error, is on the bottom of this graph, we have the control factor, and we have two levels of X. And now there's some variation in X. So you can think of X varies between a low value and a high value. And you might have some distribution between those values, maybe a normal distribution, maybe some other distribution, but X varies. It's not exactly constant. Now, if X varies and Y is dependent on the level of X, so the blue line represents the dependence of Y on X. So that's how Y changes as the X value changes. You can see that the variation in X is causing variation in Y. So if X is varying around its set point, the middle, then we see variation in Y. Now, when you have a curvilinear relationship, you can see that if I increase the value of X, now it has the same variation. But if you look at it, that variation is transmitting much less variation to Y. Okay, so basically, as the line becomes flatter, the variation in X causes less variation in Y. So that's the propagated error, the error that's propagated from the variation in X to create variation in Y. So how does it work? Well, once a relationship has been established between a factor and a response, the variation in the output can be one, dependent on the factor of the level of the control factor, or two, independent of the level of the control factor. Okay, so as we just saw, when we have a curvilinear relationship, the variation in the output is dependent on the level of the control factor. Therefore, if we set the level of the control factor to the area where the relationship's flatter, we can reduce the variation transmitted to the response from that variation or lack of control of the control factor. If we have a linear relationship, you can see that the variation in the control factor is going to be generating constant variation in the response, regardless of its setting. Okay, because it's not going to get any flatter if it's linear, so it's always going to be a constant. So let's look at a really simple example, and we'll vary two factors. We're going to vary the transistor gain. That's a nonlinear relationship to the output voltage. We're going to vary another factor, the resistance. That's a linear relationship to the output voltage. And what we're trying to do is we're trying to create an output voltage of 115 volts with the least amount of variation. So maybe we start out and we've got a certain model represented by the first black line where the gain's set at 250, which is generating our 115 volts. And then you can see from the variation in the gain, that's generating variation in the output. Okay, now what happens if we increase that gain from 250 to 350? Well, we move to where the curve is the flattest. So that greatly reduces the variation in the voltage. But now our voltage is off target. We're getting a very constant voltage, but it's a voltage of 225 instead of 215. So what we can do then is we can then go in and say, okay, well, voltage varies linearly with resistance. So what I can do is I can decrease the resistance. So our original prototype had a resistance of 500. And we're going to decrease that to 250. And that moves our target back down from 225 to 115. Okay, so the linear ones can then be used to shift back to target. Okay, so in theory, what we're doing is we're using the control factors in kind of a two-step process. First, we're decreasing the variation by looking for the flats using the curvilinear factors. Then we're trying to shift it back to the target using the linear factors. Now, not all of the time are you going to have pure quadratic or pure linear factors, but there'll be varying degrees of both. So what we could do is we can use numerical optimization to search for where we can find the target with the least amount of variation. So in practice, we're going to use numerical optimization to try and get both on target and reduce the variation. Okay, so how can we do this? So finding regions where variation of the control factors transmits the least amount of variation. Okay, so it's easy to look at a picture and say, okay, we want to be where the flats are. But how can we find those flats mathematically? Well, here's a curvilinear relationship. So we can see the relationship between the input X and the output Y is related by the quadratic equation where beta naught is 15, so the intercept is 15. Plus 25 times the value of X minus 0.7 times the value of X squared. So that gives us that line, that blue line. Okay, what we can do then is we can use the propagation of error to figure out what that is. So we can then go in and we can look at the equation, the quadratic equation, and we can take the partial derivative with respect to the x's, in this case there's only one x, and multiply that by the variance of the x. What's nice is when you've run a DOE, you've already got the equation that relates the y to the x's. All we have to do is take the partial derivative of that with respect to the x's. So there's nothing new that needs to be added, except we have to know what the standard deviation in those x's is. What's their variation of the control factor around its set point? So that's that sigma x. Okay. So then we can take the partial derivative with respect to that. Then whenever we analyze a design, we do an ANOVA, we end up with a model, and the R squared says, okay, the model explains 80% of the variation. Well, 20% of it isn't explained by the models. That's that residual variation, residual variations. We always have something that's left over that our model doesn't explain. Of course, moving the X doesn't help explain that, or it would have been part of the equation. So that has to also get added in. So we take the variation in the last equation there with the square root sign of it. We take the variation in the X's times the variance of the X plus that variance of the residual. Okay. What's nice is you need to have a general understanding of how this works, but the software will do all the math. So what is POE? So POE is the transmitted variance. So it's the variation in the X's, the partial derivative times the variation of the X's. Now the Z's represent the uncontrollable factors. Okay, so then you can also, so those are just X's in a different class. So again, you take the variation of the equation with respect to the individual Z's times the variation of the Z's, plus that residual. Now we report POE as the square root to put it back in the scale we're measuring in. So our POE, rather than being transmitted variance, is really a transmitted standard deviation, just the square root. Now what you have to do, be able to use POE, is you have to be able to supply those sigma X's and sigma Z's. You need to know what the variation of the control factors are around their set points, and what the variation in the uncontrolled factors are around their nominal value. Okay, and it's expressed as a standard deviation. Okay, so let's see how this works. Well, first I'm going to go through this example on the slides, and I'll show you how to do it in Design Expert. I'm going to be using Design Expert 13, which isn't quite ready yet, but it's getting close. And just give you a little preview of that. But you can do exactly the same thing in Design Expert 12 or 11 or earlier versions if you have one. Okay, so I'm just going to look at a one-factor design where the X is going to be varying. In this case, the X is an A from 0 to 15. Originally, I designed this for a cubic model. I sorted it by X. Notice the run order is in a random order. Of course, that's the way you'd run it. I just sorted it so you could kind of see the progression and the responses. The factor A gets higher, the response increases. There certainly appears to be some strong relationship there. Okay, so we go in and we compute the effects and we select a model. Okay, and our model comes out to be 15 plus 25 times A minus 0.7 times A squared. So similar to the picture I drew with a little bit of rounding errors. Okay. And let's go that far, and then I'll come back and show you how to enter in the sigma. Okay, so here's the design. Now I haven't sorted it, but if I sort in ascending order, you can see that's the same data that I showed you on the slide. Let's go analyze that. Okay, so a little bit different look in Design 13. There's going to be special models, more non-linear modeling. So you have to pick whether you're going to do linear or special models. But we're just going to do the normal analysis. So there's our fit summary. Obviously, a quadratic model fits really well because I made it fit really well. We're going to pick that model. We pick that model, intercept plus coefficient times A plus a coefficient times A squared. So the model's highly significant, lack of fit's insignificant. Yeah, I made the model fit perfectly, almost perfectly. R squareds are all round off to almost 1. Now what we want to look at is the actual equation, because the standard deviations are measured in terms of actual values, you know, whatever the values of your response are, and the X's, not coded values. So we can see there's our equation of 15 plus 25 times A minus 0.7 times A squared. So then that gives us a graph And you can see that, remember the R-squareds are almost 1. So you can see the confidence intervals are almost indistinguishable from the fitted model. So I made a model with no error. I did that to show that when we put the propagated error in, we're going to get some error, even though there wasn't any in the experiments we ran. Okay, so we'll go back to the slides. It says, okay, now to get propagation of error, you have to enter in the standard deviation for each factor. We're going to use a standard deviation of 1 for factor A. So on this graph, if I go up to view, and I want to view propagation of error, it's grayed out. There is no propagation of error. What do I have to do to get propagation of error? I don't have to do any more experiments. I don't have to do any more analysis. All I have to do is tell it what the variation in A is. So I go here and I just change the view from the design layout to the column info. Okay. And you can see that when we do designed experiments, an implicit assumption is the factors are known without error. We know that's never true. The set points might be without error, but there is error around the set points. Okay, so I'm going to put in a standard deviation of 1 here. Once I do that, and I go back to the model graph, you can now see that the error that's propagated from that variation in A, those lines are no longer superimposed on the fitted model. Okay. Now I can go up to view and I can look at propagation of error. Now, if you notice what happens, well, remember this was that curvilinear relationship, and as A increased, the variation transmitted from the variation in A to the response decrease. So we can see that this is showing that the variation that's transmitted is decreasing as I move from a low value of A to a high value of A. Now, if we look back at the model graph, you can see that here too. Notice that at low values for A, the confidence interval for the predictions is much wider because there's more transmitted variance than it is at high levels of A. Okay, so doing the propagated error and having the ability to look at the transmitted variance and look for where that's lower comes at a very low cost. The only cost is not more experiments, not more analysis, just figuring out what the expected variation in the inputs are, knowing those signals. And many times you can get those from existing gauge R&R studies or literature, or do a little study and estimate them yourself. Okay, so we saw the fitted model, took the partial derivative with respect to that model. We supplied the sigma of 1. The residual variation was 0.95. So that comes from back here in the ANOVA. There it is. The standard deviation that's left over after fitting the model is 0.9473, or I rounded off to 0.95. Okay. Now you can also go to the point prediction and see what that error is. Okay, so if I go to the point prediction, okay, now that 14.5 is the error when the A is set to its midpoint, 7. Now remember, that's going to be dependent on without. So here we've got the predicted response without POE. Okay, so that's got that residual standard deviation of 0.95. Here we've added the propagated error. Now, if I go to low A, that propagated error should get bigger. So I'll drag A to its lowest value. We can see at its lowest value, that's 25. Okay. If I drag A to its highest value, that propagated error is only 4.1. Okay. Okay, so if the response is a linear function, then in fact, transmitted variance is a constant. Okay, so if you just look at that, if I have an equation where I've got a linear response, well, what's going to happen when I take the partial derivative with respect to this? Take the partial derivative with respect to that, that drops out, that gets multiplied by 1. I get a value of 25. Doesn't matter what x is, there's no value of x. So it's just a constant times the variance of x plus the residual. So the model would follow this green line. The propagated error would be a constant following this maroonish, purplish line. Okay. And now we can see that the standard error is just bumped up by a constant. And if I varied x, it would just remain 25. Okay, so it's increased by the fact we're accounting for the extra variation, but it doesn't change. It's not a function of x. Okay, well now let's look at an example of how to put this to use. So what I'm going to look at is I took an example from one of our workshops, and we have a company, a precision machining company, that's having trouble holding nominal values on their new highly automated lathe. So your job is to study the process and reduce those variations around the nominal value we're trying to achieve in the part size. And previous work on lathes in general have told us what the key influencers are likely to be. They're going to be cutting speed, and from experience we know a pretty reasonable range to study, feed rate, same thing, and depth of cut. So we have 3 factors, and we have a pretty good idea that the optimum values are going to occur in these ranges where we can hit the target value, the nominal value of the part size. But what we want to do is find conditions where not only we hit that nominal value, but we hit it very consistently. In other words, we reduce the variation around what that's going to be. Okay, so what design's appropriate and what model should we design for? Well, the experimenters in this case said, well, we expect quadratic behavior. We think it'll be a pretty smooth surface in the ranges we selected. We're confident the optimum is going to be within that region. We can't really operate the lathe steadily outside those regions. So in this case, the region of interest and the region of operability are very similar. They don't want to exceed those stated values. They want to fit a quadratic model. So they chose a design that would fill that space and allow them to fit a quadratic model without getting any points to fall out of that space. And they chose what's called a box banking design. Okay, so that's just a special kind of a 3-level design so we can fit a quadratic model where all the points fall within a cube. And the response is the delta. So we're trying to hit a nominal value. So delta is how far off the nominal value are we, measured in thousandths of an inch. Okay, those are called mils. So the ideal delta is 0. And delta can either be positive, the part's too big, or negative, the part's too small. Ideally, it'll be 0. Okay, so I'm going to open up a design and we'll go do the first part of this, and we're going to fit an appropriate model, and we're then going to look at the response surface and see if we can at least do the functional design, that is, achieve a level where delta is 0. Okay, so if I go and open up this design, there's their box banking design. They have 3 factors. If you look through here, each of these 3 factors has multiple levels, okay, so that we can fit the quadratic model. So I'll just sort one so you can see the the 3 levels. So we've got levels of 330, 515, 700. So each one of these factors will have 3 levels that'll allow us to do this. I'll just sort the response. Sending, you can see we made a lot of parts that were too small, some that were pretty close to nominal, and some parts that were bigger than nominal. So that's good. It looks like we've found where we can make a 0 somewhere in this space. Okay, so let's go analyze this. So this is suggesting we use a quadratic model. Now that cubic model's aliased, we can't fit it, but we can estimate some cubic terms. But when we look at those cubic terms, they don't seem to really add anything. They're not significant, and they don't increase the adjusted R squared. So it looks like we'll go with that model. If I go to ANOVA, I can see that that model is highly significant, lack of fit's insignificant. I've got a good agreement between adjusted and predicted R squared. They're high. I have adequate precision. But if I look through here, I can see several values that are not very significant. So I might want to reduce the model. So I can go back here, and I am going to reduce the model. Otherwise, it won't quite agree with the slides I've got. So I'm going to go in here and reduce it using the AICC corrected criteria and backward selection. Takes out 2 terms. Those are the 2 terms we saw that weren't significant, BC and B squared. Accept that. Model still significant, lack of fit's insignificant. Good agreement between adjusted and predicted, adequate precision. Now this is real data. I could look at the diagnostics. There does seem to be one point that's a little bit different than the others, but if I look at it over here, that's the highlighted point. It doesn't seem really unusual, and it's not all that influential, so I'm not going to worry about it. Now I can go to model graphs, and if I look at this, notice there's a contour of 0 here. That's what I want. So I could operate on that contour of 0. Now remember that there's a third factor, so that's really a lot of different contours of 0, because that's a curve cutting through. Think of it, it's like some kind of curve cutting through a 3-dimensional space, causing a surface of zeros. Okay, so where's the best place to operate on that? Well, as far as the functional design, anywhere gives me a 0. But what we want to know is there's somewhere on there where I get less variation transmitted from variation in the inputs. Okay, so to do that, we're going to need to add POE. Okay, so now we know we can do the functional part. Let's look at this part. Okay, so now we're going to enter the information. These are the standard deviations of the factors around their set points. There's a 5, a 0.00175, a 0.0125. We can enter those, and then we can do propagated error. So let's go do that. I go back to the design, and again, change the view to column info. Those values were 5 for A and 0.00175 for B and 0.0125 for C. If I go to this, I don't have to analyze anything. I can go back here. I could look at the view, and now I could do the propagated error. And these numbers are little, so I'm sure you can't read them, but the colors go from red, which is the highest propagated error, to blue, where it's the lowest. So you can see that this is a slice through the middle in the AB plane. I'll do a slice in the AC plane. There's a slice in the AC plane, and I can do a slice in the BC plane. There's a slice in the BC plane. So you can see there's definitely areas where the propagated error is lower, than it is in other areas. And so what we'd like to know, is there an intersection where the propagated error is low and we still get a target of 0? So how can we do that? Okay, so there's our propagated error plots. We can go do the optimization, and what we could do is say, well, what I want to do is I know what the specs are. The specs for this part were nominal plus or minus 0.4 mils. So I could go in there and I could say, okay, I'm going to look for where the CPK, remember CPK is just a measurement of how far you are from the closest specification in number of standard deviations. Okay, so I'm going to go in and try and do this optimization. So I can go to the numerical optimization. I can go in here to the delta, and I can change my goal to be CPK. Now CPK takes into account both target and variability, remember. So I don't really have to do anything there. I do have to put in the specifications. The specifications were minus 0.4 to plus 0.4. And I want to maximize CPK. I can go for the solutions. And let me look at the ramps. What it does then is it's trying to maximize the CPK. Now I don't have to include POE in the optimization because POE is used in calculating the CPK. Okay, so maximizing the CPK should drive it to target and drive propagated error low. So you can see that our delta is driven to target. Remember, we wanted 0, we're getting 1.6 times 10 to the minus 8. So that's 0. Okay, so we're driving the target to 0. Plus, you can see we're driving the POE low. So we're going to the lower range of the POE. So we did find a point of intersection where we can be on target with low propagation of error. Okay, and that's the settings of the factors. And I like the ramps because I can immediately see where each of the factors fell within the range of the factors I studied, within what range they varied over. Okay, but the CPK we got is still low. You know, it's low. So what we'd like to do is we'd like to reduce that. So one of the things we could do is we could say, okay, we could invest in some money in the lathe and we could do a better job of controlling the input factors. So I could reduce that standard deviation associated with the input factors. How should I spend that money? So what we want to do is we want to find out where is our variation coming from. So we're going to partition the variance of the inputs. Okay, so again, we've got a model. So this is just writing down the equation for a model for the predicted response. Okay, then we've got the transmitted variance. That's what's again just a partial derivative of the x's with respect to the x. Okay, I did that because that illustrates the idea. Actually, in the software, it goes on and takes the second derivative and the partial derivatives for the cross products of the x's and does some other things to make it a little more precise. You get 95% of the value from this first term. As far as reducing variation, this is all you need. But if you want to get unbiased estimates of the y's from the response, then you have to add this other part in. But the software does all this, you don't need to worry about it. So we just simplified this a little bit to illustrate how it works. Now, normally when you have residual variation, so the variation of the residual comes from the variation in the part itself, the variation in the measurement, and variation due to our model not fitting. We're gonna, if the lack of fit's insignificant, we can assume that's negligible, so we'll assume it's 0. Okay, so again, our residual error is going to be due to variation in the parts, variation in the measurements, lack of fit. So lack of fit would be significant, means I didn't fit a good model. So if I fit a linear model here, the lack of fit, the variance is 191. And that's caused by the fact I fit the wrong model, because when I fit a squared model, that sigma lack of fit goes down to squared, or variance goes down to 0. So all we're saying is you can't do propagation error if your model doesn't fit, right? Because we're just using the model to decide where the flat areas are. If your model doesn't fit the data, well, then you can't do functional design, nor can you do robust design. So you have to fit an appropriate model. Okay, in this case, we had a really good fit. Lack of fit was 0. So what we're going to do is to partition the variance. We're going to take the variation we've got, and we're going to say, okay, well, how much of that's due to just sigma, the unexplained variation? How much of it's due to factor A, the variation of A around its set point? How much of it's due to B around its set point? How much of it's due to C around its set point? So to do that, what I'm going to do is I'm going to set each one of these to 0, and then go back and calculate what the propagated error is at the optimum point. Okay, so if I set S to 0, I can see that the variance is reduced by 31.7%. So a lot of the variation seems to be background noise, experimental noise that's not accounted for by variation in the X's, and it's not accounted for by my model. Okay, if I set the standard deviation for A to 0, I can see then that that accounts for 1.1% of the variation. So spending money on better control of A isn't going to help. If I could control A perfectly, I can only reduce the variation by 1%. So it doesn't make any sense to spend money on A. Okay, so I set A back to 5, and now I set B to 0, and I see that I can reduce the variation by 11%. Well, that's still not very good, but we can see that a large part of the variation is caused by the variation in C. When I set C to 0, then I can reduce the variation by 56%. Okay, that's accounting for the majority of the variation. Okay, so if I look at the percentage that the overall POE is reduced by setting each of the factor standard deviations to 0, it's going to be 56 for A, 32 for S, 11 for B, 1 for A. So it looks like making an investment in reducing C would be good. Now, if I can't get there by reducing C, then what I have to do is I have to look at S. Now, S is that part of the variation that's unknown. So I'd have to go back and start investigating, saying, well, what's causing that variation that wasn't part of my design? Okay, there's something going on that wasn't part of my design that's causing it. Maybe I have to retrain the operators. Maybe I have to get better control of raw materials. Maybe there's something else, better maintenance on the equipment. You know, there's something going on. So that would be much more difficult to address. Okay, so I go in here and what I say is, okay, I did some work and I found out I could improve the control on A, and I think I could improve the control so I could reduce the variation in A in half. Okay, I'm not going to be able to make it 0, but I can reduce it in half. What's that going to buy me? So I'm going to go back and I'm going to reduce this by half. I'm going to see what that does to my CPK. Okay, so I go back to my design and I'm going to reduce this by half. So that would be 0.00625, was it? Yeah, 0.00625. Okay, so I just changed that. So, okay, I'm gonna have less variation in there. Now I could go in here. Well, I don't have to go in here. I can go to the numerical optimization. I can rerun it. Okay, unfortunately, I was able to get up from a 1.1 to a 1.5, so I quit looking. So I'm going to go back here and say, well, I want to see if I can get farther than that. I'm going to just change the upper limit here to be 2. And then go in here and look at solutions. And nope, I can't really get much past 1.5, but that's a pretty good improvement going from 1.1 to 1.5. how did I achieve that? Well, all I have to do is invest some money so I can reduce the variation of factor C around its set point. So some different kind of controller for factor C probably. Okay. So if you go to the point prediction, after running the optimization, it brings it to the optimum. You can see we've got this better. So CPK is going from 1.1 to 1.5. That's a good improvement. The question we have to ask is, okay, we think we can reduce that in half. We have to get the controller, see if it really does it. How much does that cost? Is it worth the cost? And remember, a 1.5 is not bad, but it's not Six Sigma. If you're searching for Six Sigma, you want a CPK of 2. And you can see that, remember, our specifications were minus 0.4 to plus 0.4. If you do a tolerance interval, remember, a tolerance interval is an interval that contains a certain portion of the population with a certain probability. So we're doing a 95% confidence on a tolerance interval that contains 99% of the population. We'd like that to go from be within the bounds of minus 0.4 to plus 0.4, and it's 0.45 minus 0.45 to plus 0.45. And that's because our CPK doesn't really have us up to Six Sigma. If this was Six Sigma, all of these would be within spec. Okay, so those are all things for you to consider. So that's my webinar. I did finish up a little early. I haven't really been looking to see if there's been any questions or if Sherry's been answering the questions. But I'd be glad to answer any questions you have for the next 10 minutes or so. All right, so you missed, someone asked, I missed where to set S equal to 0. Okay, so if I go back to Design Expert and remember when I changed this and said I'm gonna set it to be half? Remember before it was 0.0125? And I said I'm gonna reduce it to be half. I could have said I want it to be, oops, get one key at a time, I want it to be 0. Now, if I could reduce that variation to 0, boy, we should be able to do really well then. Of course, that's not practical to reduce it to 0. You know, now I'm going to get to be a Six Sigma process, right? I'm up to a CPK of almost 2 in my 95% tolerance interval. For 99% of the population is inside that minus 0.4 to 1 plus 0.4. Okay, but you know, we could never get it to be 0. We thought we could get it to be half. Okay, but that's where you'd enter it. Let's see if there's any other questions. If you have a transformation on there's a question about what do you do if you have a transformation on the response. You don't have to do anything. You have to actually have to do a lot of math, but that's all taken care of in the software. Okay. If you want to know more about that, I'd have to think of what a good source would be. I guess we used to have some of that in our workshop materials, but I'm not sure it'd be worth you digging into it. It's just a lot of math to do the inverse transformation to get the POE back in the right scale. See if there's any other questions. Depending on the Depending on the set point, that is not constant. I'm not sure what the question is. I mean, here, what we're doing is saying we have a set point. Our set point could be anything in the range we studied. The set point doesn't have to be a constant. You might want to expand on that question and send it to Stat Help. I'm not sure I understand it. There's a question here about what if we're using a specific weight ratio in a formulation? Do you think it'll work? I'd suggest if you're doing a formulation, do it as a mixture. And we do have POE built in to work with mixture design. Again, the math is a little bit different. The ideas are exactly the same. But that's all built into the software. So if you do it as a mixture problem, it should be okay. If you do it as ratios, as long as you know what the variation in those ratios are, it'll work that way as well. And you'd have to know what the variation in those ratios are. Okay, somebody's asking about how do you account for variation in the unknown factors like ambient temperature. I didn't have time to really go through how to do POE for the uncontrollable factors, but to very briefly state it, you'd have to be able to control the uncontrollable factor temporarily during the DOE. So, for example, I actually did a study where we were looking at some rheological properties and we were concerned about ambient temperature. We actually put the rheometer inside of a environment where we can control the temperature, and so we were able to control the ambient temperature while we were running the experiments. Now, we did that so we could fit that into a model, and then we could do the propagated error for that. Now, what's different is when you go to do the optimization, now you've got a model that's got control factors, which in real life you're going to control, and you've got this factor ambient temperature, which you control during your experiment, but you're not going to be able to control in the real world, but it's in your model. So you put that in, and you put in what its variation around its nominal value is. Excuse me. What's different is when you go to do the optimization, for any of the uncontrolled factors, you just set them at their nominal values and you don't let them vary, because they're going to be at their nominal value and they're going to vary around that. You don't have control over that. And so then what it does is it includes the transmitted variance from that factor. If that factor is involved in any interactions with other factors, that means the levels of the other factors will determine how much of that variation from that uncontrolled factor gets transmitted to the response and gives you an opportunity to reduce the variation due to variation in the uncontrolled factor without controlling the uncontrolled factor. Okay, so basically you just have to treat it like a controlled factor during the experiment. You have to be able to control it so we can build it into the model. Then once the experiment's done, then you treat it as a factor you can't control. Okay. Someone's asking about using a central composite design instead of a box spanking. You could do that. In this case, since we had the levels of the factors out to their minimum and maximum value. You wouldn't want to extend the axial points or star points in a central composite design beyond those. So you'd have to use a face-centered central composite design where the axial value is plus or minus 1. That would work fine. The POE doesn't depend on the design, has no effect. The POE depends on the model. So you have to run a design that allows you to fit a model that fits your data. But you don't have to worry about what design was used as long as you get an appropriate model. Just looking here to see if there's any other questions I can answer quickly. Someone asked if artificial neural network function will be included in Design Expert 13. The answer to that is no. I'm not saying that wouldn't be a good thing to have, but I know that's not on the list. Here's somebody answered their own question. That's good. If uncontrolled factors cannot be controlled but can be recorded, is there a way to add those as covariates in Design Expert? If you add them as covariates, you're not going to be able to do POE. What you could do is just add those in, let me show you on this design. If I go back to the design layout, I could insert a factor here. Maybe this is room temperature. And I've already got the data, and I know the room temperature is going to vary from 62 degrees to, oops. Going to vary from 62 degrees to 70 degrees. Then what I could do is I could just enter those values in. As I enter those values in and get the rows all done, then I'd be able to go back and reanalyze that with as a factor and then treat it as a non-controlled factor. Question, how do you suggest to estimate a factor standard deviation? There I'd refer you to just look up information on gauge R&R. Okay. And that'll give you techniques on how to estimate variations of different devices. Someone asked an important question. What if the variation around a set point at 25 degrees is smaller than the variation around the set point at, say, 100 degrees? An assumption in doing POE is that the variation is a constant. I don't know of a good way to handle a case where the variation is not a constant, other than to transform that factor, and you'd have to do that externally to Design Expert. So, for example, if you put in the log of the temperature rather than the temperature itself and the standard deviation of the set points around that, that would automatically make the standard deviation have a bigger effect at higher values than it does at lower values. Okay, so you could do temperature that way. It's something it'd be nice if we had in Design Expert, but right now we don't. So I think that's about all we've got time for now. So I'm going to end the webinar. I do want to thank everyone who attended. I didn't get to all the questions, and if I didn't get to your questions, please send those to StatEase, stathelp@statease.com. And thank you very much for attending.